3.
Okay, so now let's talk about part 2. So in part 1 we talked about the intuition of least square, the basic intuition of alpha, the beta, and how we find the regression line. So, but the most important part is probably intuition. How would you use? See, all of this is now done in the software packages. A computer program can do this, and it'll give you the output. So you can find the data for the hours the students had for exam, the score that they got on the exam, and put it in a computer program, and it'll give you the results. I mean, there's so many programs now. Stata, eViews, MATLAB can do it. Yeah, I don't even try to list them all. But the output they give you is very similar, and you need to know how to. You should be able to interpret the output that they give you. So any program will give you something like this. So they will give you a constant or an intercept, something like that, and it's going to be our 20. It will also give you a coefficient. Coefficient, this is a slope we had in the previous part. That was the beta. So this was 10. Another thing they'll give you is they'll give you your standard error. Standard error. So the way you calculate standard error is, remember, they take the sum of all those values. This, they take this, they square it, add this, square it, sum it all up. Later on they'll divide it by number of observations minus 2 and take a square root of that. Just write it down on the board. But so this is standard error. The key point here is that it's really dependent on how closely the line fits between our observations. If observations are really far out here, then standard error would be large because this number would be large. So the one thing they'll give you is standard error. Another thing they'll give you is, an important thing is t-statistic. T-statistic. And all t-statistic is that's your coefficient, or a value for intercept, divided by your standard error. So that gives you a t-stat. Divided by the standard error. Okay, so why are we bringing up all this stuff? Because whenever we get this regression line, we get the beta, we get the constant. We want to know we want to know how certain they are that there is this relationship. We want to do we're going to do a test on it. We're going to do a two-tailed test on it to see whether that is statistically significant. So that's why we're calculating the t-statistic. And remember that the t-statistic, the larger the t-statistic is, the less likely the more likely our outcome is we can reject the null hypothesis. And what is our null hypothesis in this case? It is that the beta, or the coefficient, or the intercept. But I'm just going to talk about the coefficient. So the coefficient is equal to 0. That's our null hypothesis. So let me write it here. So this is our null hypothesis. The beta is 0. Beta 0 means this is this. There's no relationship. There's no relationship between hours studied and the score on the exam, because that's what beta 0 implies. And we're going to use this test statistic to see whether we can reject this null hypothesis. And we get the statistic by using the size of the coefficient plus the standard error. And remember, whenever the larger the test statistic is, the more likely we are to reject. The more likely we are to reject the null hypothesis. So generally, say we get usually around 2, when the statistic is about 2, we can reject the null hypothesis at 5% significance level. So let me remind you what all that is about. Let's squeeze the graph in here. What that would say, if this statistic is about 2, then then the likelihood that there is a more extreme T is only in this area. Only in this area. So we can reject the null at this significance level. Now the larger the T gets, the larger, the smaller the probability that there is a more extreme teams that are even more extreme. So if the test statistic was maybe like 10, we'd be way out here. And this part would be really small. This number would be a lot smaller. This would be a lot smaller. And that would mean that the T's that in this distribution, the values that are more extreme would be even less likely. So that would help us reject the null hypothesis. So the larger the T statistic is, generally should be larger than 2, we should be able to reject the null hypothesis that beta equals to this. There's no relationship. So that's what this statistic does. But it's not really that easy to remember the size of the T statistic. It's not really that easy. What is the T statistic of 6, say? What is it? Of 10? Plus, it depends on degrees of freedom. So there are more convenient ways to use the p-value. So in sometimes some statistical packages will call it probability, but most will call it p-value. And p-value gives you this number. It gives you the probability of having a T in this distribution that is more extreme than the number that we are getting. We're getting is this T statistic. And the lower that number is, the lower the probability of having more extreme number than we're getting here, the easier we can reject the null hypothesis. So p-value is easier to interpret. So if, let's say, we got a T statistic of around 2, we'd have a p-value of around 0.05, meaning that 5% is around here. If a p-value was 0.001, that means only really few, there were really few more extreme T statistics than we were getting. So we could really safely reject this null hypothesis that the slope is this. Okay, there's one more thing I want to mention. It's the R squared. Right in here. If the R squared is high, R squared tells you how closely the observations are to the line. R squared is between 0 and 1. It's between 0 and 1. If every observation is perfectly aligned on the line, then the R squared is 1. It's perfect. Every observation is right. This difference is non-existent. That's 1. If I don't know, when R squared, it probably is never 0. But if they're really weak, all the observations here, all over the place. Then R squared would be very small or close to 0. The interpretation of R squared is, the larger R squared is, the more reliable the results are. So in sum, if you know how to interpret the intercept, you know how to interpret the coefficient, and you know how to test it for statistical significance, then you can just take any computer package, put in your data in a software. It'll give you this output. It'll give you the other stuff, but it'll give you this for sure. And then you can make inferences about the data that you're messing around with. And here I just had one variable. You could actually put in more than one. You can put something else in there. It'd be harder to show it on the graph, but for a statistical package, they can handle more observations. So it doesn't have to be one. You have to have only one dependent variable, but you can have many independent variables. So, okay, so this is it for part 2, and I'll just do part 3 for the drawbacks or